All right, so what I will tell you about now is beyond trees. So this lecture is kind of independent in a sense of everything else. There won't be mirror descent at all in this lecture. One of the open questions is whether you can somehow do what I'm going to do now with mirror descent. That would be really amazing, and I believe it's maybe doable, but I don't know how to do it. Okay, so beyond trees. Metric embeddings. Okay, so you remember the situation is that if the metric is a tree, then we can run mirror descent on it, and we get a competitive ratio of depth times log n. And the question is how to go beyond that, how to work, for instance, let's say on a line. If your graph is just a line, then the depth is n. Okay, so you don't get anything out of this argument. So we're going to talk about metric embedding. So what is a metric embedding? So we say that x embeds into y with distortion d. Okay, so these are two metric spaces. Okay, and this is some positive number. So I use this notation if there exists a map f from x to y that does not change too much the distances, okay, such that for any pair of points x, y in x, if I look at the distance of the image of those points through f in y, so the distance in y between f of x and f of y, this should be comparable to the distance in x up to a distortion factor of d, okay? And up to a normalization of the distance in y, I can just always assume this is bigger than 1, and this is going to be smaller than capital D. Okay, so the distances do not change too much. They change at most by a multiplicative constant. That's what a metric embedding is. Okay, so why is this very useful for online algorithms? So it's very useful for online algorithms because of the following. So assume, so if this is the case, so if x embeds into y with distortion d, and we have an alpha competitive algorithm in y, okay, so typically y, we're going to look at y, which is a tree metric. Okay, so we already know, say, depth times log n competitive algorithm for y in that case. Then I want to say that you can transfer this to get an alpha times d competitive algorithm for x. So why is that? I can just run my algorithm in y, and this gives me some movement in x. Now, what is the movement in x? So I know that the algorithm in x, okay, so the movement that I suffer in x, this is certainly smaller than the movement that I suffer in y. Okay, this is this non-contracting property. Okay, the distances in y are just bigger than the distances in x. So if I record the movement cost of my algorithm in y, I just record a larger movement than what is actually happening in x. Okay, so this inequality is true. Now, by alpha competitiveness in y, I know that this is smaller than alpha times opt in y. And now, because the distortion is at most capital D, I know that whatever movement I record in y for opt is at most capital D times the movement in x. So this is at most alpha times D times opt in x. Okay, so out of the combination of an alpha competitive algorithm in y and a metric embedding with distortion d from x to y, I get out of both of these things, I get an alpha d competitive algorithm in x. Right? The movement cost of the algorithm in x is bounded by alpha times d, the opt in x. Is that clear? Okay, so it's all about finding embeddings like this. Yeah, please.
Sorry. How do you go back from y to x?
So this, it's like it's a bijection on the image of f, right? Because just it's non-contracting, so they always have to be distinct. Yeah. So really, you can think it's just, I mean, x and y's are not really different. Like the distances are different, but if you want, the background set is the same. It's like just the distances are different. Any other question? Okay, so the problem is, in general, there are no good embeddings into trees. So, problem? If the cycle of length n, okay, so just the cycle of length n, if you embed this into a tree with distortion d, then d must be omega of n. Okay, so this is a theorem. I mean, it's very obvious intuitively, but by Rabinovich and Ranraz from 98. Okay, so I have a cycle like this. And I want to represent this as a tree. I mean, the problem is what can I do? One thing I can do is that I can, for instance, open the cycle somewhere. But if I open it here, then suddenly those two vertices which were at distance 1, they are now at distance n. Okay, so there is a huge distortion happening at these 2 points. Okay, so we cannot realize this program. Just it's never going to work. But there is an amazing observation by, so observation, I think it's due to Karp. And it appeared in a paper by Alon, Karp, Peleg, and West. I think around the same time, so 90-ish. The observation is that instead of looking at a deterministic embedding, we could consider randomized embedding. Okay, because eventually we care anyway about randomized algorithm. So what would it mean, randomized embedding? What it means is I'm gonna, so for randomized, so there exists, so I'm gonna say the same thing, but let's say randomized. If there exists a random map, f, okay, so now f is not deterministic, such that, okay, so now this is a random quantity. I will want this inequality to be always true. So this should be true almost surely. So the map is always non-contracting. Okay, it never reduces distances. But now I want this inequality only in expectation. Okay, so again, this inequality is, I require it to be true always, and that inequality, I only require it to be true in expectation. Okay, so by that I mean the expectation of the distance in y is smaller than capital D times the distance in x. And why is that enough? Well, let's look at this sequence of inequalities. So because it's non-contracting, the algorithm in x, the movement is always smaller than the algorithm in y, which is by alpha competitive is smaller than alpha times the opt in y. And now this inequality becomes true in expectation. Okay, so if I add expectations, I get this. And now this one is still true. Okay. Why did I need almost sure here? I needed almost sure because the algorithm is going to depend on f. So this quantity depends on f. Right? Because I'm going to run an algorithm in y which depends on the random mapping f. So that's why I need this one almost surely, because I want to apply it to some quantities that depends on f. But here opt doesn't depend on f. here, maybe here, opt is independent, I mean, does not depend on f. Okay, so this inequality, it's fine to only have it in expectation, because I'm not gonna, there will be no dependency issues. Okay, so this is the observation, and now what happens for the cycle? Well, what happens for the cycle is, say I cut at a random edge. So if we cut Cn at a random edge, then what happens? Well, the distance in y between 2 points, maybe two points next to each other, I and I plus 1, this is either 1 or it's n. So this is 1 with probability 1 minus 1 over n, and it's n with probability 1 over n. Right? Because the probability that this distance is distorted by a factor n, it only happens if I exactly cut that edge. But this only happens with very small probability. So this implies that the expected distance is just 2. Okay. So this gives me a randomized embedding of the cycle into a tree, namely a line, with distortion 2. Okay, so you get like infinite improvement over the deterministic case. Yes, please.
But the line is the worst kind of tree to embed into.
Yes, absolutely. Yes. I mean, for what we have in mind. But in general, maybe it's nice. But yes, sure. This is just a proof of concept. But you're right. Any other question? Yes?
Here we have a bound on the expected alg over the expected opt, which
Yes.
is the competitive ratio. What if we care about the expectation of the ratio rather than the ratio of the expectations?
Okay, so let me just think. This quantity has no expectation. You see, this, yeah. I mean, yeah. This is equal to just alpha d opt in x. Yeah. Okay, so now let me tell you the theorem that we're going to prove, which is an extremely powerful theorem. And we're going to prove it. So the theorem, so in the literature it goes by the name FRT. So this person has a name too complicated for me to remember, and this is Rao and Kunal Talvar, and it's following some work by Yair Bartal from '96. So they improve a log n over that, and the proof that we're going to see is due to Manor and Mendel and a variant of James Lee. I will explain all of those things, but the theorem goes like this. For any x, there exists a O of log n randomized embedding into a tree of depth log n. Okay. So you can, so here we had a really very dramatic improvement from n to a constant. In general, life is not going to be that good. In general, we're going to have a log n distortion, and the depth that we get is log n. Okay, so if we combine this, so for MTS, this gives, so now we get 1 log n due to the embedding, 1 log n due to the depth, and 1 log n due to the competitive ratio of, on the tree. So this gives a log cube n. Okay, but in fact, those trees are special in a certain way, and instead of depth times log n, we can get log n on them. Okay, I won't explain that. That gets a bit technical, but basically we can remove one of the log n. Okay, so the remaining log n, the one which is blocking this wonderful conjecture of borrowed-in linear sacks to be proved, is this log n from the randomized embedding. And this is, if you go the route of randomized embedding, you cannot improve that. This log n has to be there. Okay, so if you want to improve this, you will have to do something different. So the hope is this log squared n, log n times log n, it should really be log n plus log n. You should really be able to have two different algorithms that work on those two things independently, and they don't get multiplied but added, the competitive ratio of those two things. But we don't know how to do this. So anyway, I'm going to tell you now the proof of this statement. Okay? So first, so let's prove an easier version. First, we prove a weaker version. So how is it going to be weaker? It's going to be weaker because I'm going to prove O of log squared n distortion. And only for metric spaces with poly n aspect ratio. Okay, so what is the aspect ratio of a metric space? It's just the largest distance divided by the smallest distance. Okay, so for instance, if you have a line, the largest distance is between the two extreme points, which is n, and the smallest distance is 1. So it's fine, it's poly n. But for instance, I told you one of the examples of MTS was this power management, where it looks like this, right? So you can imagine, so this was on 3 points, but you can imagine generalization of this where, the next one is further away, like, it keeps doubling the distances. This is an extremely interesting metric space, and its aspect ratio is exponential, right? So every time the distance doubles, so this will not be covered by this weaker proof, but anyway, we're going to prove the real theorem also. So in fact, the real proof is going to be simpler than the weaker proof. But I want to tell you the weaker proof because at least personally, I understand better what's happening in there, even though it's a more complicated proof. Okay, so let's prove this. So what I'm going to start with is a lemma. So hierarchical partition lemma. Okay. So for any metric space, there exists a random partition Px such that all elements of the partition are small. Okay, they have diameter less or equal than delta. Okay, so delta is something fixed that you fix first. Okay, so for any metric space, there exists a random partitions with all the elements of this partition with small diameter, and such that for any fixed point x in X, and any scale r, which is not too small. So it has to be bigger than delta over poly n. Okay, so this is where if the metric space was of poly n aspect ratio, this is not an assumption to have a scale not too small. Okay, there are no scales smaller than that. But in general, here I didn't assume that it has a small aspect ratio. So for any fixed point and any fixed scale, what happens? The probability that bxr, so if I look at the ball of radius r around this fixed point x, the probability that this guy is cut by the partition, that it's not included in one of the elements, is small. Okay, so the probability that bxr is cut by px, this is small, this is of order log n times r over delta. Okay, so let's parse this. So again, I have a partition of my space. I don't know, maybe it's going to look something like this, something like that. Okay, so this is my space, and it's partitioned into elements like this. And I have some point x and a small ball around it. And I'm saying that the probability that this guy is cut, meaning it would look like this, okay, that this ball is not fully included in one of the elements of the partition, this probability is small. How small? Well, provided that the scale is smallish compared to delta, okay, smaller than delta over log n, then it's of order of the scale. Okay, so for very tiny balls, the probability that they are cut is very tiny for any such ball. Yes, please. Greater than delta over poly n. Yeah, so like delta over n to the 100. Yeah. Yeah, sorry. Please ask me if this term was not clear. I know we use it a lot in CS, but it's not, and for the right reason, it's not very used in mathematics. So by poly n, I just mean I have fixed a constant, and this is like n to that constant. Okay, and this constant is fixed forever. Yes?
For smaller r, you have much better ones?
No, I don't have anything. But yeah. So I mean, I have. Okay, I always have. Okay, no, I don't have anything. I mean, I always have like this delta over poly n. So I always have, you know, let's say the maximum between this and 1 over poly n. Like if r was exponentially small, I wouldn't have something exponentially small. I would only have something polynomially small. But again, we're going to fix that. So this, I'm going to explain the proof of this, but then we're going to do a stronger version. Okay, but before I prove this lemma, you know, the first time you see it, you're like, okay, what does that mean? Let me show how to use this maybe a bit abstract. I mean, it's not that abstract, but this weird lemma to prove this very concrete embedding theorem. Okay. All right. Okay, so proof of the weaker theorem. Proof of the weaker theorem using the lemma. So what I'm going to do is that I'm going to construct a tree by induction using this random partitioning. Okay, so I start with the root. So this is the root. This is my entire space X. Now I call this lemma, this hierarchical partitioning lemma. I mean, it's not, I don't know why I called it like this. It's not hierarchical at this point. It's just a partition lemma. So I call this lemma, and I get a partition, x1 up to xl. So this is partition lemma on X with delta equals diameter of x divided by 2. Okay, so I have 2 points which are very far. Okay, so I have a space of some size, 100. And now I'm just going to get a bunch of smaller spaces of size 50. Okay, so I get a bunch of them. I don't know how many. A bunch of them. This is this lemma. Make sense? Okay, so it's going to look like this. I get one thing like that, one thing like this. Let me just think. Yeah. So, you know, it's going to be maybe like that. So this will be maybe x1, x2, and x3. Okay, so I get a certain number of them. And now I just repeat. In there, I call the partition lemma, you know, with the diameter of x1 divided by 2, and so on and so forth. Okay, so here now, I will call it with delta, which is diameter of x divided by 4, and so on and so forth. Okay, so this gives me a tree. Now I need to put weights on the edges. Yeah, let's say. So if this happened to be already small, you know, maybe I don't cut it further. I just go one step like this. Let's say. It would be fine to put diameter of x1 divided by 2, but it's just. Okay, so now I'm going to put, so this is a tree, like a topological structure. Now I'm going to turn it into a metric space by putting weights on the edges. And the weight, I will just put weight here, diameter of x divided by 2. On this edge, I put diameter of x divided by 4. And you know at depth k, this is, say, depth k. What do I have? It's like this. So this was depth 1. So this is going to be diameter of x divided by 2 to the k. Okay, and notice that my tree is of depth log n because of the assumption on the aspect ratio. Okay, I can go at most through log n scales because once I went through 100 log n scales, I'm at size 1 over n to the 100, and there's nothing below that. Okay, so the depth is log n. O of log n because of aspect ratio assumption. Okay, so now let's verify the two things that we need to do. We need to verify that almost surely this is non-contracting and that in expectation it does not expand too much. These are the two things we need to prove. Okay, so let's prove the first one, the non-contraction. So one, non-contraction. And this needs to be almost surely. Okay, and again, this means that the distance in x, between x and y, should be smaller than the distance in the tree t between x and y. Okay, so again, here the mapping is kind of the identity mapping. I mean, the leaf is just the leaves. You know, they have their original name, and that's it. It's just, as I was saying before, it's really just the metric structure which is changing. Okay, so how do you prove that? Let's say, yeah. So say that the distance in the tree between x and y is smaller than some t. Okay. So if it's smaller than some t, then let me think. I want this. I want to say if it's smaller than t, then what happens? Why do I have a factor 2? Right. So if it's smaller than some t, then, certainly it must be that this edge was, so you have x and y, and they are distance less than t. So it must be that this edge is of length less than t over 2, and this one should be less than t over 2. Okay? So in fact, those 2 points, they are included in a partition element of diameter at most t, because that's kind of the definition. Okay? Yeah?
Why should both be below t over 2 and not just the sum be below t?
Yeah. The sum needs to be below t. So in particular, those two elements, the sum of those two elements need to be smaller than t. I mean, it's weaker. You're right. I mean, for those two things to be close, it needs to be that the entire sum, here this entire sum needs to be smaller than t. But now I'm saying, let's just say, in particular, those two should be smaller than t. If I have a plus b plus c, which is smaller than d, then a plus b is smaller than d, if they are all positive. That's all I'm saying.
Okay, but the two red points are not x and y. These are just the closest things.
These are x and y. So let's say this is the level of the leaves. These are the 2 points that I'm trying to measure distance between. I fix them. And now I just want to say, okay, let's assume that the distance in the tree is small. And all I'm saying is that it must mean that they are in a partition element of small diameter. Okay, so again, say that this distance is smaller than t. This implies that x and y are in a partition element at some level of diameter less than t, which implies that the distance between x and y is less than t. Right, this is the diameter in the original metric space. Okay, so this means that this guy is smaller than that one. Right, any upper bound on the first one is valid for the second one. Okay, so this is always, so basically what this is saying is that this type of construction is always going to be non-contracting. It's just always going to be non-contracting as long as you have this element which have small diameter. Okay, so that's all this is saying. This is not using the lemma at all. Now we want to look at the expected distortion. So expected distortion or expected expansion. And now we're going to use the lemma. Okay. So what do I want to say? All I want to say is the following. So all I want to say is, yeah. So if x and y are cut at depth k, okay, so if these 2 points, they become separated at a certain level, then what do I know? Then, okay, why do I say it like this? Let me just think. BXR, probability that it's cut. Yes. Okay. So if x and y are cut at depth k, then the distance in y between x and y, what do I know about it? Wait, that doesn't make sense. I'm confused. If they are cut at depth k, what happens? Yeah, I guess. So if they are separated, then I know that this is big. I see. Yes. Sorry, y is a tree. Y is a tree. Yeah, so I want to say if they are cut at depth k, then if this is the first level at which they are cut, then the distance is in fact equal to the diameter of x divided by 2 to the k. Yeah, it is bigger. I agree with you. Yeah, that's the problem that I have right now. Yeah, it is bigger. What? Up to a factor 2, it's smaller. But they could have been cut at a higher level too, no? Why am I confused? Yeah, I think this is what I need to say, yes. Yes, I think this is what I need to say. So if x and y are cut at, yeah, okay, yes, okay, I see, okay. Okay, so if x and y are cut at depth k, and not depth k minus 1, okay, so if this is the first scale at which they are cut, then in fact, yes, this is exactly twice, it's exactly twice the sum over all L bigger than k. Okay, good, of this, right? So this is the first scale at which they are cut. Then the distance between those two things, I need to sum, this entire path. Okay, so I sum over all L from k to log n, say, of diameter of x over 2 to the L, and I get 2 because I have those two branches. Okay, I will explain why I was confused. It's very simple. It's very stupid, but which is whatever, 4 times the diameter of x over 2 to the k. And now, finally, I use this lemma, okay? And the probability that they are cut at depth k for the first time, it's certainly smaller than the probability that they are cut at depth k at all, okay? So the probability that this happens is of order log n times r over delta. But what is delta? Delta is diameter of x over 2 to the k. So this diameter of x over 2 to the k cancels with the 1 over delta. And you're just left with log n times r. And what is r? You apply this to r, which is the distance between x and y. Okay, so let me say this again. Okay, so this implies that the expected distance in t between x and y, this is smaller than the sum over k of the probability that x, y, this segment is cut at depth k, times diameter of x over 2 to the k, and with a factor 4. And here I use the fact that it's actually equal to probability that xy is cut at depth k for the first time, and the probability that they are cut at depth k for the first time is bounded by the probability that they are cut at all. And this probability is because of this log n times dx between x and y. So this is O of log n times dx between x and y. I apply the lemma with little r, which is just the distance between x and y. times 1 over delta. And what is 1 over delta? It's 1 over diameter. Delta is diameter of x over 2 to the k. Okay, so those two things, they cancel. And what you're left with is O of log n times dx between x and y. Okay, and here I used again this aspect ratio because I use the fact that this distance is not too tiny. It's bigger than 1 over poly n. Oh, yeah. There is a, of course, log squared. Thank you. Yes, there is a sum. Yeah, of course. There is a sum, which is the number of levels. And I did say the depth is O of log n in this construction because of the aspect ratio. So I get only log n terms in this sum. Yes, very important. Every term in this sum is of order log n times dxy. So the sum over all of them is log squared n times dxy. And this is what we're going to improve. We're going, when we do the proof of the more elaborate version of this. Okay, so you see, once you have this partition lemma, it's just 2 lines. I mean, 1 line for the non-contraction and 1 line for the expansion. Okay, to get the distortion. So in a sense, like all the magic, all the difficulty. I mean, there was a lot of difficulty in coming up with that argument, but now all of the difficulty is pushed to this partition lemma. Okay, so let's prove the partition lemma. Okay, so proof of the partition lemma. So I'm going to do it by induction. So assume we already have x1 up to xi minus 1 included in capital X. And they are all of diameter bounded by delta. And now I will tell you how to build the next element of the partition. So now pick arbitrarily some xi which is not covered yet, which is not in the union of those things. Okay, pick some element which is not covered. Pick a random radius Ri, which is smaller than delta. I will explain what kind of random radius we want. And now what I do is that I just take the ball around this little xi of radius Ri, and that's my new capital Xi. Okay, and of course I carve out everything else that was already there before. And set Xi, which is the ball centered at little xi of radius capital Ri minus the union of the xj for j less than I. Okay, so the picture is like this. I first pick a point, some point. I grow a ball. Then I pick some other point. I grow a ball, maybe that one. Then I pick some other point, maybe that one. I grow a ball. I pick another one. I grow a ball. Okay, and I keep this process. So if I were to combine this picture with that one, you see what I would do is then, at the next scale, I would pick a point here, grow a ball, pick a point there, grow a ball, etc. So it's this kind of multi-scale hierarchical partitioning. It's very beautiful, I think. Okay. So now how do I pick this random radius? So what I'm going to do is a really beautiful trick. I'm going to take it from an exponential distribution, and then I'm just going to use the memoryless property of the exponential to prove this bound. Okay, so amazing trick. Pick Ri from an exponential distribution. Okay, what do I want from this exponential distribution? I want it to not go above delta. So of course, maybe it will go above delta, but if it goes above delta, I want this to happen only with very small probability, like 1 over n or 1 over poly n. Because if it happens with small enough probability, remember I said, really, because of the assumption that R is at least delta over poly n, you can replace this by saying this is for any R, but then I want the max between that quantity and 1 over poly n. So any event of probability smaller than 1 over poly n, it doesn't matter for me. Okay, so if I want an exponential distribution to go above delta with probability 1 over poly n, what I should pick for the parameter is log n over delta. Okay, say of order of this, some constant. So this implies that the probability that Ri is bigger than delta is 1 over poly n. Okay, and if you want, if this happens, if at some point one of your ball grows too big, then you can say you just enter some failure mode, and you say, okay, then I give up and just I assign every point to a singleton. I mean, my partition is just all singletons. So say on this event, just return all singletons. Okay, and again, this modification of the procedure, it just add, a plus 1 over poly n in this probability estimate. Because of course, if everybody is a singleton, then all the balls are cut. But it's just a 1 over poly n added factor, so it doesn't matter. Okay, so let me assume that I'm on the event that everything is nice, and in fact, I don't even need to worry about that. Let's just say I pick a radius which is like this. Now, if I pick a radius like this, why is this statement true? Okay, so let's call this star. So why is star true? Of course, what is an exponential, right? You all remember this? An exponential distribution of parameter lambda. This is just a PDF proportional to e to the minus lambda x. Right? X is non-negative. Right, this is an exponential distribution. So of course, so the CDF is also of this form, e to the minus lambda x. So if lambda is log n over delta, and x is like delta, then I get e to the minus log n. That's why I get the 1 over poly n, just to be sure we're all on the same page. Okay, so now why is it true? It's just kind of a picture. So I have x, and I have my scale r, and I have some xi here, and the beautiful thing with the exponential is you can think about it like growing like this, right? It's growing, it's growing, and the point is, why can you think about it like that? Is because if I say, okay, I know it's bigger than this ball, then it's memoryless. So it's again an exponential after that of the same parameter. That's the whole point. So when is this ball going to be cut? This ball is cut if I know that it got to this point, but then it stops within distance r. Okay, so the probability of a cut, that bxr is cut, this is, let's say, by xi. What is this? This is smaller than the probability that the exponential is smaller than little r. Right? I need my exponential to stop in a window of size little r. That's what I need to cut these balls. But what is the probability that an exponential is smaller than little r, it's 1 minus the probability that it's bigger than r, and the probability that it's bigger than r is e to the minus lambda r. So this is equal to 1 minus e to the minus, so the parameter, which is log n over delta, times r, okay, which is bounded by this. Right, 1 minus e to the minus x is bounded by x.
This is just for an x which is the center of the ball that you drew, not for any x interpretation.
What? Say again?
Right? This is for the x you originally chose as the center of the...
No, this is for, no. That's no, very important. I use the memoryless property. So I use the fact that I'm growing a ball somewhere here, you know, and I care about this ball over there. The only way for it to be cut is that my exponential is growing. You know, if it stops before it reaches the ball, then it doesn't cut the ball. For it to cut the ball, it has to reach the ball and then stop, you know, in a window of size little r. So I can just condition, I can say, okay, I reached the ball, but now I stop in a window of size little r. Right? So this is true for any other point. Yeah? Okay, good. So now, so this finishes the proof of the weaker version. So now let me tell you how to change things to get the strong version. You don't need to change many things. So, yes, please.
That's for one xi.
Yes.
So how do you go to...
To all of them? Yeah. So I want to say, let me think. I want to say this is just a union bound. Let me think. So
The first I such that you keep the ball E of xr.
yes. Oh, that's right. Yes, exactly. Yes. Thanks, Thomas. Yeah. So just think about, you know, they are all growing simultaneously. And now you just take the first, you know, at some point one of them is going to reach the ball BXR. And now you argue about that one. You know, you condition on everything that happened at that time. And now you say, okay, this is the one who is going to decide the fate. You know, either that one, it includes the ball, or it cuts it. Make sense?
Or even sequentially, those that stopped before, they leave it in the game, but you would need to consider that.
Right, yes, you can also say that, yeah. In fact, what I just said was, okay, yeah, never mind. Yeah. Yes, very good. Yeah, so it's not really a union bound, it's slightly more clever in a way. Okay, so now the very beautiful improvement. Okay, so let's do the improvement. So the improvement is the following. So improved partition lemma. The same is true for any r. Okay, so now you don't need the scale constraint. The probability that bxr is cut by px, now instead of being log n times r over delta, is going to be the following. It's going to be of order r over delta times log of, and instead of log n, we get this thing. The size of a ball centered at x and of radius delta divided by the size of a ball centered at x and of radius delta over 8. Okay, where did this n come from, right? That's what I like about this proof, is that this log n, it's pretty clear where it came from. I mean, one reason is just you needed this to have a union bound over all the radii. Okay. But now, instead of having, we're only going to look at things which are likely to threaten the current ball. So the picture is like this. I have this ball of radius little r. And what I'm going to do is that I'm going to make sure that my radius, Ri, now it's going to be between delta, let's say delta over 2, and say delta over 4. It doesn't matter. Okay, so it's not going to be too small. It's going to be between two deltas. So the point is, for this to be cut, something has to happen between there are two balls that are. So this radius is capital R minus little r. And now you have a bigger radii of capital R plus little r. Okay. So the point is, for this to be cut, it has to be that it's cut by somebody in that region. Okay? Because if you get somebody here, because the radius is capital R, you know that it's going to contain that one, that ball. If it's outside, then it cannot even reach that ball. Okay, so the points here, like a ball that starts over there, cannot cut this. A ball that starts inside can only contain it. So the only points that threaten this little ball are the one in this shell here. Okay, so you only get log of the size of this shell. And the point is, okay, so I will explain how to prove this in a second. But if you have this improved lemma, then you see in the calculation of the expected expansion, what happens is that instead of this log n, you get something which is summable. You know, you will get the sum of the log, and you know, it will be like, view this as log of, you know, maybe let's say log of uk over uk plus 1. Okay, so you have the sum of log of uk over uk plus 1. Okay, so this is summable. This will be just log of u0 minus log of un, something like that. Okay, so instead of paying for every level, you pay just a certain number for every level, and all of those numbers, they add up to log n. Okay, so instead of this log squared n, you will only have log n out of it. Now, how do you prove this improved lemma? It's a simple calculation by just picking Ri. So now you pick all of them to be equal and uniform in that interval. Okay, so it's even a simpler distribution. You just pick one radii for everybody, uniform in that interval. And now the probability that you, and there is one more modification, very important. Here, I picked xi arbitrarily. Now here is a smart move. I'm going to pick xi at random. Pick xi at random. Okay, and I will just write one inequality and conclude with that. The one inequality that I want to write is the following. So again, the construction is I pick a radius uniformly at random between delta over 2 and delta over 4. And I will do this carving process. And the way I do it is that I first pick a point at random. I put the ball there. I pick a point at random which is not covered. I carve the ball, and so on and so forth. And what I want to say is the probability that bxr is cut, or maybe is not cut, this is at least the size of bx r minus r, capital R minus little r, over the size of bx capital R plus little r. Okay, why is that? It's again this reasoning that I told you before. So if when you pick points outside of this ball, they cannot threaten my little b, x, little r. They just cannot cut it. So the only points that are going to decide the fate of this ball, whether it's cut or not, are those in that ball. So I can condition on only looking at what happens when I select one of those points. And the point is that if I select a point from here first, from inside the small ball first, then I have saved my little ball. Because if I pick a point from this white ball, it will contain the tiny ball inside. Okay, so as long as I pick a point here from this set before picking a point from the complement of this set in that one, I'm good, I'm saved. Okay, so it's not cut with that probability. And now you just need to look at the expectation of this thing. And it's a calculation, like an exercise of first-year probability to compute this expectation. And you will find this. Okay, so that concludes this part. Is there any question? So I should say, yeah. So again, so the result itself is by FRT, which is an improvement over Bartal. This argument is taken from Manor, Mendel, and Asaf Naor, and with some improvement by James Lee, and you can find all of this on the blog by James Lee. He has a very nice blog post on all of this. Yeah?
The expected distortion, right? Started by log factor.
Yeah.
Do you know anything about this concentration as well? Or like how much can it vary from this computation?
Yeah. Yes. Let me think. I mean, it's a delicate question in general. I mean, you can think about just the case of the cycle, what happens in the cycle. So, you know, with small probability, 1/n probability, you have this huge distortion. So, you know, that's one phenomenon that you can have. Yeah, I don't know in general. I don't know if there is an answer in general. Yeah. Okay. Thanks.